Hello everyone. In this video, we are going to understand the post correspondence problem, usually called PCP. It is one of the most important undecidable problems in the theory of computation. What makes PCP especially interesting is that it looks like a very simple word puzzle, but in reality, no general algorithm can solve all the possible cases. In this presentation, I will explain the intuition, the formal definition, a solvable example, and an unsolvable example, leading to the fact that this problem is so important in computer science. So, what is PCP, the post correspondence problem? The post correspondence problem was introduced by mathematician Emil Post in 1946. It is a famous example of an undecidable problem in computability theory. That means the problem is very easy to state, but there is no universal method or algorithm that can always give the correct yes or no answer for every possible input. PCP is also very important because it is widely used in proof. In formal languages and automata theory, many other undecidable problems are proved by reducing PCP to them. To understand PCP intuitively, let us look into the problem. Imagine a set of domino-like tiles, but instead of dots or numbers, each tile contains a string on the top and another string on the bottom. You are allowed to use these tiles in any order, and you can reuse the same tile as many times as you want. Your goal is to arrange a sequence of tiles so that if you read all the top strings together from left to right and all the bottom strings together from left to right, both complete strings become exactly identical. Now, this is the central puzzle of PCP. Now, let us look at the formal definition. Suppose sigma is a finite alphabet. We are given two lists of strings of equal length called A and B. The first list is A equals U1, U2 up to UK, and the second list is B equals V1, V2 up to VK. A solution to PCP is a sequence of indices I1, I2, IM up to IM, where M is at least 1, such that the concatenation of the selected strings from the top list is exactly equal to the concatenation of the selected strings from the bottom list. In simple words, by choosing the same sequence of indices in both the lists, we must obtain the same final string. Let us now see a solvable example. We have three tiles. Tile 1 has top string A and bottom string ABA. Tile 2 has top string AB and bottom string BB. Tile 3 has top string BBA and bottom string A. Now, a valid solution is the sequence 1, 2, 3, 1. Now let us check it out. On the top, we get a plus. On the top, we get A plus AB plus BBA plus A, which gives the string AABBBAA. On the bottom, we get ABA plus BB plus A plus ABA, which also gives the string AABBBAA. Since both top and bottom strings are identical, this sequence is a correct solution. So this PCP instance is solvable. Now consider another set of tiles. Tile 1 has ABC over AB, tile 2 has CA over A, tile 3 has ACC over BA. Now let us think about how a match could begin. The first tile must start with the same beginning on both top and bottom. So tile 1 is the only possible starting point because ABC and AB begin similarly. But after choosing tile 1, the top string becomes ABC while the bottom becomes AB. So now the bottom must somehow catch up by adding the missing letter C. The problem of this problem is that every top string in this example is longer than its corresponding bottom string. That means the top continues to stay ahead and the bottom can never fully catch up. So no matching sequence can be formed here. Now, why is PCD undecidable? This brings us to the key idea, undecidability. Undecidable does not mean every individual PCP puzzle has no solution. As we saw in the previous example, some puzzles are solvable. Instead, undecidable means that there is no single algorithm that can examine every possible PCP instance and always halt with the correct answer. If a solution exists, a brute force search can eventually find it. So in that sense, PCP is Turing recognizable. But if no solution exists, the search may continue forever. The machine cannot know whether there is truly no solution or whether it simply has not searched long enough yet. That is why PCP is undecidable. You may wonder why PCP is so important. The answer is that PCP is extremely useful in undecidability proofs. Since it is based on strings, it is often easier to transform into grammar and language problems than directly working from Turing machine descriptions. By reducing PCP to other questions, researchers have shown that many important problems are undecidable. So, for example, ambiguity of context-free grammars, equivalence of grammars or language generators, and whether two grammars have a non-empty intersection can all be linked to PCP-style reasoning. So, PCP acts as a bridge for proving on the limits of computation in formal language theory. To summarize, the post correspondence problem is a simple string matching puzzle based on the pairs of the strings. Even though it is easy to understand, it is algorithmically undecidable in the general case. This makes it one of the most important tools in theoretical computer science. PCP helps us understand that some problems cannot be solved by any universal algorithm, and it continues to play a major role in formal languages, automata theory, and computability. Thank you for watching.